ended. That is, to summarize, if the f dash equation is of fifth degree, then there is no analytical solution, closed form solution, like you have for a quadratic, cubic, or quartic, or equations, right? So, on this took people some hundreds of years to prove. Actually, all that is very interesting history, which you can read on Wikipedia. Then the other reason is, when you have very high order functions like here, you don't have formulas to solve them. So even if you take derivatives, no use. So you need gradient, you need numerical methods. So uh, to explain, uh, the concept is, you choose one initial guess point. Can you please mute? All of you mute.
Yes, sir. Sir, actually, your screen is not presentable.
Oh, okay, okay. Sorry. In
Yeah.
between.
Thank you, sir.
Yeah, yeah, yeah. Thank you. Is it okay now?
Yes, sir. Yes, sir.
Yeah, yeah.
Thank you.
Thank you,
Thank you,
thank
sir.
you. Your
Thank you, sir.
your name? Your name?
Hello. Sir. This is Gaurav
Hello.
Gadge. I'm from Polluti Engineering College, co-host of the STDP.
Correct, correct. Gadge. Right, right.
Okay.
Thank
Thank
you.
you, sir. Thank you.
Thank you, Gadge. Hmm. So, what you have to do is, you have to go in downward direction, right? So, what is downward direction in a solution landscape? To explain that, I have I have two figures. One is the 3D picture of that function, this sin x1 plus cos x2, and the other is the contours. Suppose this is x1, this is x1, this is x2. The contours in that, I told you how contours are similar to what you already know, like isotherms, isobars, isoates, etc., from high school level. So, what is this downward direction? So, somebody also said how you identify the gradient of a function. It represents the direction of maximum increase. So if you want maximum decrease, then you need to go in the direction of minus of gradient, opposite of gradient. So if g is gradient, then minus g is the direction you need to follow. Give me now and then, you have to give me a break of few seconds, because the software is a bit slow to load, to go to the next screen. Okay, so now we have that gradient. Okay, 1 minute, let me also see the next one. So we have, okay, so now that we have here, I have taken a very simple function. So if you take somewhere here, you have to go downwards, means like this, or if you are here, go downwards, means like this. Or if you are here, for example, all these contours are in the, as you go outwards, the value of the function increases. This function is x1 square plus x2 square. Okay, very simple function I have taken. Actually, you don't need numerical method to solve this, but when trying to learn something, you have to take a known problem. Only after that, with some problem, somebody is saying stop presenting. Who is that? Some disturbance, is it? Gadge, you stop presenting. Somebody is saying
Okay. Yes, sir.
hello.
Yes, sir. Sure.
Some mistake.
Sure, sir. Sure.
No, no, some mistake. Huh?
Yeah.
Stop presenting. Some messages there.
Yeah.
I can
Yes, sir.
continue
Yes, sir.
now.
Please continue.
Oh, okay, okay, okay. So you need to go in. See, this is the positive direction G. So the D is equal to minus G is, D is equal to minus G is opposite of that, like I have shown here. So if you go in that direction, we'll reach the minimizer, minimum. Okay, so that is the concept. But a human walking in downward direction is very different from a method procedure or algorithm going in some direction. There are quite a few issues involved in that. For a some mathematical method to go in downward direction. First issue is okay. The last issue is when do you stop? Okay, that's a very big problem. For a human, that's a very easy thing to know when to stop. But for a method or algorithm, to know when to stop is a very difficult thing. Next thing is okay. The first issue is direction. Okay, first issue is direction. Second issue or okay, last issue is when to stop or stopping criterion. The second issue is how big a step do you take? Okay, so that can also be a problem. For a human, that is not a problem because human step is very small, right? If you're lost in a valley or in a mountain, the size of the steps that you take in downward direction is very small. You cannot increase that, but in simulation, you can increase that to any value that you want. So you need to definitely say what is the size of the step that you need to take. Okay, so all these numerical methods have this, let us say for now, the two main issues even before you start is what direction and what step size. All right, so they are the two main issues. So the equation you think is like this. All that we do given some x of k, where starting point is k equal to 0 means x of 0, that is the initial guess solution. So if you have x of 0, if you have x of 0, then you need to go to x of 1. Okay, so how you go is you go in the direction of minus g of k, and simply going in that direction is not enough. You need to decide the step size, how big a step you are going to take. Okay, so just to understand the issues involved, let me go to the MATLAB program now. Because multiple screens or whole screen is cannot be shared, some I think it will waste some time, so I have to switch between the screens and MATLAB. So now I will switch off this particular software screen and go to the MATLAB screen. Okay, so please be patient. Again, even in MATLAB, I don't know how it will share the figure. Share, turn on. And net connection is somewhat of a bit slow. Entire screen. Gadge, you have any idea why it's not allowing me to share the entire screen? That option is disabled now.
No, from my side it is still open.
No. Entire screen it's not allowing to share. See, if I share entire screen, I can show both this presentation and MATLAB simultaneously.
Sir, you
But it's
okay?
not allowing.
So, is there any other option showing? Like you have
Window, one window. It's allowing me to share one window.
one window. Fine. Actually, you are not the host, no. So I do one thing. I just make you a host so that you can present all the screens at a time.
Yeah. Thank you. That will be
Yeah.
nice.
Just
Can
a
you
second.
please make me a host now?
Yes, sir. I made you host. So now I think you can have multiple presentations. So your entire screen can be presentable now.
Wait. No. Even now it's not allowing. Have I become co-host now?
Yeah, you are a host.
Entire screen. Oh, okay. So doesn't matter. We'll try to manage.
Fine, sir,
Tomorrow's
fine.
session, we'll try to
Yes, sir. Fine,
fix
sure.
that. Fix that.
Sure.
So now I have gone to MATLAB. Okay, this morning I showed you one why exactly you need to have both theory and practice, knowledge of both the theory and practice. So now let us go to one demo. I'll show you. And also remember, one of the uh, inputs I received was you should show what it should be hands-on. Okay, so hands-on. Wait 1 minute. So with the, I know that this disturbs a bit, disturbs the flow a bit, but it might also interest people, right? So I'll show you one demo now of this GDM. Okay, so alpha, you remember our step size was alpha. So as a trial, let me put alpha is equal to 0.1. So what are you seeing now? Are you seeing the figure window also? That way? Or seeing only the code window?
Yes, sir.
Are you
Yes,
seeing
yes,
the
yes, yes.
figure
I
2?
can see your. I can see the figure. It is 0.10, point 0.1, the value of alpha.
No, no, no. Other than that,
Only
there are
workspace
figure.
is visible.
No, only one workspace, sir.
Oh, okay. So again, I have to stop. I have to do that. Okay. I will. Okay. So I have to do something. So now you are seeing this figure.
Yes, sir.
It's
Now I can
loading.
see
Sorry. I think that's a
figure
bit
two.
of issue we have to fix because if you want one session where you can also present both software and how it works and presentation, we need to do something. So you
Yes.
think this is that function f equal to x1 square plus x2 square. My starting point is 120, 25. X coordinate is 1, I think. Y coordinate is 25. So this is GDM. That fixed step size value I have entered as 0.1. Okay. So next, how does it go? So you see how it goes. It looks like, see the step that we are taking looks like very small, right? So see it run. It looks very small. So it takes a long time, right? You see that it takes a long time. What improvement can we make to this? So obviously one improvement that we can make is we can try to increase the step size. Okay, so let me try to increase the step size. So I'll run MATLAB again with a different step size. Okay, let me say I'll put it as 1.05. Okay, last time I put as 0.1. Now let me be ambitious and try to put a step size more than 1. Again, I need to mm, share a window. So now again I have shared. Now with different step size. Okay, if I use a step size 1.05, this is my result. Okay, or in other words, instead of going to, obviously you can see that it is not working, right? So you just blindly cannot choose a step size. Okay, so what might be a good value or maximum value? I'll show you that. Let me run the simulation again and then show you. So this is going to take some time, but Even if you got some idea of all this, it would be worth the time spent. Okay, because I have to repeatedly switch. So this is for a step size of 0.95. Okay, so if it is 0.95, okay, even 0.95 is too much, I think. 1 minute. 1 minute. Hmm. Okay, so something going wrong here. I'm also not able to do that quickly because I'm more engaged in it. Give me 1 minute. Okay, or will what continue with this presentation. Leave that to be figured out later. The substance of what I want to tell you is there is a maximum step size. Okay, there is a maximum step size that you need to uh, be less than. That maximum step size is given by 2 by lambda max of h, where h is the ACN. So how you get this ACN is you approximate the function by some q for quadratic. It can be written in this form: half of x transpose ax minus b transpose x plus c. If you have this q in this form, then g is ax minus b and h is a. So if you think this algebra is a bit difficult, think of like this: q is equal to half of ax square plus bx plus c. Think of the scalar equivalent that probably we all know from high school level, or at least 11th 12th. Okay, q dash or first derivative is ax. Okay, minus, you put minus here. Q dash is ax minus b. Q double dash is simply a. So you think vector, this is a vector equivalent of that quadratic equation. Okay, that's the what equivalence. So the a or the h that you get from here by approximating the function as quadratic. So from there you get the h. So the step size at any iteration should be less than this 2 by lambda max of h. So to know what is h, I need to go into that program, then I need to open. But let me give you a quick attempt. That is GDM demo 2. On one side, there is a lag from MATLAB. On the other side, net is a bit of a lag. Multiple screens sharing is a bit difficult. So altogether, I think technology has not kept pace with technology has what still to improve a little, I think. Okay, so Let us go to the next example. Okay, so what was happening when I put alpha is equal to 1, 1 or 0.5 or something is that step size was too big. That's why the method, the GDM, okay, this is gradient descent method. It uses a fixed step size. This method did not work because the step size was too big, more bigger than uh, what it could have been as per this formula. Okay, there is mathematical proof. Some people have proved, etc. But we did not worry about all that. So, if this is the upper limit for maximum step size, lower limit obviously is 0. If it is 0 means then you cannot go to the next point at all. So, in between these two extremes, there must be one optimal step size, right? At which the algorithm will work best. So it will converge very quickly in least number of iterations. In least number of iterations, right? So what is that step size? Optimal step size for alpha, which will converge to the minimizer in least number of iterations, right? So that formula and that method which uses optimal step size, that optimal step size method, the grade descent method, the gradient descent method that uses optimal step size is known as steepest descent method, STM. Okay, and the formula for alpha k is given by here. Is given here. There is a simple derivation, a two-line derivation. Maybe we need not worry about that. So let us see how steepest descent method works now. So there, that is more. I don't have to give the step size, so hopefully that will run faster. Only thing is, again, I have to share. I have to go out of this PPT, share that again with you, so that stop sharing, then share again, share window. I have to do.
Sir, it's okay because this is our also hands-on session, so it needs some time. So it is quite okay, sir.
Oh, thank you, Aparna, for that. So now I have showed you now for x1 square plus x2 square, the optimal step size is zero point 0.5, and if you choose that 0.5 you can reach the minimizer in just one iteration. Okay, so as you are seeing in the screen, the function is same, x1 square plus x2 square, as compared to GDM, this took many iterations. For x1 square plus x2 square, you can reach the minimizer in just one iteration, right? So, what do we conclude from this example? We have found a numeric answer to all our optimization methods, the problem of optimizing. So, to understand that, let us take another function. Let me take another function. Instead of x1 square plus x2 square, let us take f equal to 5x1 square plus x2 square. It is visible here on the right side. The contours are visible. You see that now the solution space, the contours are not circles but ellipses. Okay, and you can see the three-dimensional figure of the solution, the function versus x1 x2 also here, left side. Okay, so how does the SDM, steepest descent method, work on this function? Let me show you that. I have to share now. Stop present. Then share a window. Then okay, but note now for x1 square plus x2 square, it converges in just one iteration. Keep that in mind now. Okay, please keep that in mind. Now I'll show you for pi x1 square plus x2 square what is happening. You see that like GDM took lot of iterations, you remember. Now even SDM is taking same kind of many iterations. I'm not able to show you because my screen is very small. I mean, that particular screen is very small. Okay, zooming this up, zooming in. Okay, again, software is a bit slow in that. Are you? Oh, again, 1 minute. Okay, so this is the best that can be done. But I wanted to just catch the point that for x1 square plus x2 square in one iteration, the SDM converged because the contours were circles. But now when the solution space is ellipse, then it is taking more iterations. Okay, so that's the message. So why is that? And not just this, let me take another example. Let us take a solution space that is having even more narrow kind of values. Narrow kind of values like I have shown you here. Okay, so hopefully you wait, it's loading. Okay, so now it is there. So how does it behave? Okay, so you see here, even with the best step size, it takes much larger. Okay, so hopefully now it is more clear, I think, or bigger picture at least. Right, so the more oblong or the more elliptical the solution space is, the more the number of iterations that the method, gradient method is going to take even with the best step size. Right, so why is that happening? That's the question now. So the why it happens is because if you are starting from here, you think we are going in the direction of steepest descent. You remember? So solution, if my x star is somewhere here, we are not going in this direction. Now we are going somewhat in this direction, then again back in this direction, and so forth. That is why you get this zigzag going from left to right, like this, like this, like this, like this, like this. Because this is the direction of maximum descent, what I am showing you. Not from here, if my x star is here, if somehow I can go in this direction, then I can I'll reach there easily. But my steepest descent direction is here, like this. Right. So that is why it is taking so many huge number of iterations. So how do we now I have shown you picture so you can understand the problem, but otherwise how do you make out? Okay, so this kind of problem is said to be ill conditioned. Okay, so yeah, what method where all problem where these work easily is known as well conditioned. This is known as ill conditioned. Okay, so how do we differentiate between a well conditioned problem and a ill conditioned problem? So we have a measure of that, that is condition number. Condition number is not something that applies only here, it applies in general to matrices. The condition number of a matrix is the ratio of the maximum eigenvalue to the minimum eigenvalue. And now in this in optimization, the condition number of SCN, that determines how well the problem is suited for solving by SDM. Okay, so condition number for 100, the SCN for 100 x1 square plus x2 square is lambda maximum is 200, lambda minimum is 2, so this is 100, which means the lower the condition number, the better condition it is, and because 100 is a huge number, that is ill condition. So for a problem, for a ill conditioned problem, SDM will not work as well as it works for a well conditioned problem. Steepest descent method, that is very important, because in engineering you can have quite a few ill conditioned problems. Your method might be fine, perfect, theoretically perfect, okay, but in practice, because the problem is not that well suited, it will not work that well, right? So that problem is there. So is there any remedy, any better method? So people, okay, all this is something historical, you think, historical, okay, so what, based on continuous efforts of lot of people, inputs, analysis, all these things are done. So let us look at Newton's method. The next method that we look at is Newton's method, whose formula, recursive formula, is given by this: x of k plus 1 equal to x of k minus h inverse, okay, hk inverse, it should be hk inverse x of k into g of k. All right, the same 100 x1 square plus 100 x2 square, in which SDM did not work that well. We'll see how it works on this. Okay, so that is going to take time, or okay, you should see at least once, then you can. Seeing is believing, right? So I will switch between here and there. Okay, so same figure is there. Okay, this figure, same figure is there, so I will not switch there. So you see that Newton's method can reach in just one iteration from any starting point for a quadratic function. Okay, for a quadratic function. In other words, Newton's method is independent of condition number of the function, if the function is quadratic. Okay, so because of that, from anywhere, let this be some very large distance, starting point away from x star, even from there, in one iteration it can reach, if you are using Newton's method. So the difference is, so what's the difference? Why is it happening? Now, okay, sometimes we ask how to apply some method. Sometimes we have to ask why the some method works better than the other method for that particular problem. Okay, so coming to that why part, so why does Newton's method work better than STM for the same function? Okay, so why does it work? So you note that the direction in this was minus g. In steepest descent method, the direction was minus g. In Newton's method, direction is So people, are you listening?
Yes,
Are
sir.
you okay? Only Aparna is listening. Others, anybody else, any other voice?
Yes, participants.
Okay, so that's okay. Wait. So let me continue. So the point is, the direction here is minus h inverse g. Alpha step size is 1. In Newton's method, the step size alpha is 1. The direction is minus hk inverse g. Okay. So because that direction is towards x star, you are able to reach in one iteration. That direction is known as Newton's direction. So you see that when we started initially, I told you the two issues even before you start applying some method is one is direction, other is step size, right? So direction also makes a lot of difference. Step size also makes a lot of difference, right? So by using Newton's direction, you can easily reach x star in one iteration, even in a ill-conditioned quadratic problems. Okay, but quadratic problems are not where you need to apply Newton's method. Now we are simply trying to understand the methods GDM, SDM, Newton's method. Okay, so that's why. So that means have we found the answer to all our optimization problems? We can blindly apply Newton's method wherever we want and it will solve the problem for us. Can we say that is we have found the ideal method for all our problems? That's not the case. So once again I have to go to MATLAB, then come back to this and all that. So I'll show you that. Okay, so now I have to share. Sorry, wait 1 minute. So this is for a function you think. So this is for a function. My starting point is here, okay, 0. Now applying Newton's method to this function, what do I get? So from my starting point, I reach some star. Star value means what? That's the optimizer. I can't go any further than that. That's the meaning of that. So I put that symbol star for that. So from x of 0, this is for a single variable function as you can see. X is on x-axis, on y-axis you have function. So single variable implementation of Newton's method where x of 0 is 0. I have reached x star in one iteration. Okay, so because now I have to close this, I have to go back. You have a good look at this because now I'll go out of this. Okay, now what is the problem with this? I have started with some x naught. I have reached the x star in one iteration. So it looks like what everything is fine, but it's not fine because okay, I have to stop switching like that repeatedly. So I'll stick to only the presentation. Okay. That's not fine because my x of 0 is here. Okay, this is the graph of that function. Okay, now I'll explain. I can also show this in MATLAB, but because that's repeatedly switching and takes a lot of time, I'll skip that. I'll try minimize doing that. This is my x of 0. Okay. Now my x of 1 I found is here. Here. My gradient at this point is also 0. If you want to verify, the function is here. Function is here. So f dash equal to g, you can find out. Substitute 0.75 there. That will show you that g or f dash at 0.75 is 0. Which means I have reached minimizer. I have reached optimizer. That's what you will think, but it is not optimizer, but a saddle point. As you can see from this graph, it's still increasing. It's a saddle point. So why did Newton's method not work in this for this particular problem? Right. So that issue is there. So to understand that, I think I have one more program, but somehow I have to skip that, I think. So let me directly go to this. Okay, so to understand that, you look carefully at this. The blue is the function. Then the second one, brown, that is the derivative. Then the yellow, that is the second derivative. F double dash. For a multivariable function, that is the SEN. So what is happening here at x of 0 is, you note here at x of 0 is, what is happening here is, this double derivative is less than 0. The yellow, you note the value of the yellow there, that is less than 0. Or in other words, this hk is less than 0. Or in other words, that is negative definite. Okay, or all eigenvalues are less than 0. If that kind of thing happens, then this will not work well enough. It will not work. It will go in opposite direction. Instead of descending down the function and reaching minimizer, it will go in opposite direction. And if h is or f double dash is less than 0, negative sign instead of being positive sign. Okay, so that's what can go wrong in Newton's method. And not to forget, when does a SCN, when can you invert a SCN? Are there situations where you cannot invert a SCN? Participants? Okay, now and then I'll take a small breather by depending on saying, okay, participants, are you there? Are you listening? Etc. Okay. Okay, so I'll proceed. There are actually passive participants. Okay, people who don't want to, what, some are reluctant to say something. So let me continue. The inverse is defined as adjoint by, okay, adjoint by determinant. Okay, so if the determinant happens to be equal to 0 or the SCN happens to be singular, then you cannot use, obviously you can't have H inverse because dividing by 0 you can't do, right? Thank you, Aparna. If the determinant is 0, then you cannot invert the matrix, and that kind of matrix is known as singular. So singular matrices cannot be inverted, and if H happens to be singular, definitely you can't apply the method. If it is non-singular, you can apply blindly the maths, and but if H is less than 0, or it has only all eigenvalues less than 0, then it will go in the opposite direction instead of the correct downward direction. Okay, so that is another that is the problem with Newton's method. So what is the solution to that? The solution to that is this is Newton's direction, you remember. You should somehow make this hk greater than 0 instead of less than 0. Okay, so how you make that greater than 0 is by adding one lambda k into I, where lambda k is a scalar. I is a identity matrix of the same order as H. So if you add this lambda k I to hk, if lambda k is large enough, then hk plus lambda k I will become greater than 0. So that the direction will become again downward. Okay, so that kind of method, or people who see anything that we do is not the result of any one man's work, that too one brilliant idea working for one, what some lightning striking a man and getting a brilliant idea. Only after engaging with the problem for a very long time, or lot of people thinking about it, solutions come. So think that finding out this problem with Newton's method and remedying it, all that took some time. The contributors being this Levenberg Mark I. Okay, so that kind of modification done to Newton's method so that it can successfully find the minimizer. That method is due to these people, Levenberg and Marquardt, and that method is known as LMM method. Okay, so that's the next development you think, but again we have a issue. See, it is never ending story in life. If there is a poor man, you think, who is on the street struggling even for one meal, one day's meal, all that he'll want first is somehow he should get food for all 3 times a day. Once that is assured, next thing he'll want is, okay, I need a house, he'll think. Right? So I need a roof over my head. So once he gets that roof over his head, again next thing will happen. Okay, this house is too small. I need some minimum standard of living. I need better kind of food. Right? I need better clothes. Right? So again it will expand always. The requirement, the minimum requirement or what is needed will go on increasing. So same with even all these optimization methods you think, because I might have demonstrated all these concepts to you by taking the simplest possible problems for understanding. But otherwise, real life problems demand that kind of treatment methods that will work well so that you can solve easily, quickly, or that kind of situation. For example, if you let us go back to my own missile guidance problem, which I showed you in the beginning. Let me take some time to go back to that. Okay, so this is that where I told you about that. Okay, so you think you are you are attacker or defender? You are either here or here. Wait 1 minute. Either you are here or here. Okay, let us think we are defender. Whether you want to conserve energy or hit in minimum time, by spending any amount of energy. That decision you have to make in very small time, in maybe in seconds. The order of the time that you have is in seconds, right? And not just that, you also need decision should be made means you have to calculate. Okay, this is not simply going to hit like this. You have to predict his trajectory. He has to predict his trajectory, and you can't shoot here. If you shoot like a bullet, the bullet will reach very fast. But even bullet fire, if you point at this current position, what will happen is by the time it reaches here, he might have moved a little. Correct? So same thing happens even in missiles. So if he is moving like this, you have to you also need some time to go and reach there. So at that time when you reach there, what will be his position that you have to predict. And after the predicting, you have to take all these decisions like whether you minimize time or minimize energy or a combination of both. Then you have to calculate how to minimize these both, right? So that's not a, and all this you have to do in a few seconds. You have to do all this in a few seconds, not that somebody has given you a whole day saying you calculate, afterwards we do, right? There are problems like that where you can take days together, even weeks together, months together if you want, and solve some problems, right? But this is not that kind of problem. And not just that, some problems, okay, the problem, if you have more computing power, then you can solve that quickly, right? And just for that reason, you are not going to put on supercomputer here in this system, right? There is no space. Even if there is a space, you cannot put a supercomputer there. So the onboard computing power is very small. The time also is very small. The dynamics is also very fast. You know that missiles travel at the speed of sound or often many times the speed of sound. For example, the BrahMos missile, okay, which India has produced in collaboration with Russia, that is having a max speed of something like 5 times the speed of sound, are known as hypersonic speed. Not supersonic, but hypersonic, right? So in that kind of situation, you need to calculate, you need an algorithm that does calculation quickly without asking for too much of calculation and without asking too much of computing resource, right? So all these requirements have to be met if you have to solve the problems, a real life problem successfully and quickly enough. If that solution has to be useful, okay, quickly enough. See, after the missile has come and hit, if I say that I have a solution, no use. If that is to be of some use means, then only when it is still about to hit me, I have to hit it. Preferably, okay, on this side of the border, right? So that is the demands that real life optimization problems make, and that is they are the requirements that methods have to meet. And why we came to all this question is, for a if I have to apply Newton's method, in every iteration I need to calculate this SN. Okay, so that's the very first requirement. And it is not enough if I calculate the SCN. I also have to calculate the inverse of the SCN. You imagine, okay, let us take electrical power systems itself. Okay, so in the load flow and all those problems, many of them, you know, if you are okay, there is a Newton-Raphson method of load flow, which is but maybe Raghunathan used that method to do load flow, so his name got attached to that. That is NR method. Otherwise, in optimization, what we know from optimization side is it is a Newton's method. Okay, so in that Newton's method, suppose I have 66 buses, you think, IEEE 66 bus system. In any bus, my variables are P, Q, V, and delta. In this, I know two of them. I need to calculate the other two. Okay. So in 66 buses, into 2 you think, yeah, into 2 you think, 66 nodes, sorry. Okay. So into 2 is 132. So if I have 132 variables, in a PQ bus, P and Q are known and V and delta you calculate. In a PV bus, P and V are known, Q and delta you calculate. So anyway, you have to calculate. Two are given, two are known, two you have to calculate. So for 66 buses, sorry, correct, that is buses. If I have 132 variables, if the SCN is of size 132 by 132, and in every iteration I need to calculate, how will I get a solution quickly? And not just SCN, I also need to invert the SCN, right? So it's not like Newton's method is the answer to all of our optimization problems. Okay, so again we what people started searching for. In addition, okay, so what can happen even in load flow studies is it may never converge at all, Newton's method. Whatever be the reasons, there are multiple reasons. You all have what go and look at all that. But it's not that what Newton's method will always guarantee solution or it will do that quickly enough. Okay, so because of that, again, people search for what might be a better method than that. So there methods that need not use SCN, okay, or at least not need inverting the SCN. That kind of methods people saw that. So in that, for example, now there is another method. Okay, this came only in 20th century, conjugate gradient method. So it doesn't need at least a H inverse to be calculated, and okay, with refinements, even H need not be calculated. So conjugate gradient method is one of the best methods now. Okay, the best methods, maybe even better than Newton's method, but not it in every electrical what power system textbook you think. Okay, so how does it work? So we'll give an idea of that. Maybe after that we'll stop. Okay, depending on Aparna. Right. So you note this. For whether you noted this or not, I am not sure. If you want, I'll run it again. In SDM or GDM, the directions that we used, were all orthogonal. Means if this was my direction in kth iteration, in k plus 1th iteration, I took a direction that is 90 degrees to this. Then again, this is 90 degrees to this in parallel with this. Then 90 degrees to this and in 90 degrees to this and parallel with the previous one. That is how we proceeded in Newton's in gradient method, whether it was GDM or SDM, or the dot product of those two, G of k and G of k plus 1, was equal to 0. And the direction being minus G of k, the dot product of D of k and D of k plus 1 was also equal to 0. Okay, so that's what we did in gradient methods. Now let us try to see how that can be improved, or how what variations people did in that. Now in this dk into d of k plus 1, in between I can insert one I matrix, identity matrix. Like multiplying any number with 1 doesn't change the product, or multiplying or even dividing does not change the product. We can also do the same thing here. Introduce one I here, so that but it doesn't make a difference, right? Adding one I. Now the idea is, instead of I, you can add another H, a H having properties like I. For example, in optimization, the property of I that we are looking at is, it is positive definite. All its eigenvalues are greater than 0 and equal to 1. That is identity matrix, right? A diagonal matrix with all entries 1, which are also the eigenvalues. Now instead of that I, you can add another. We may as well try to insert one H which is positive definite, or in other words, the only requirement is H should be positive definite like I, and nothing else. It need not be diagonal like I. Okay. So if we can find a positive definite H like that, if we have some direction, we can find another direction which satisfies this equation. Di transpose H into dj equal to 0, where I is not equal to j. Right? For comparison, you compare with, for example, SDM. Okay? So in SDM, okay, so how do you get this d of I? Like in Newton's method, you calculate in gradient methods, you calculate g. Okay, then you d is equal to minus g. Then you also know the h of that function. You know the h, you know the d. Using these two, you calculate d of k plus 1 by substituting in this equation. Now, these directions dA and dj are h conjugate. Directions gk and gk plus 1 are orthogonal. So you might think that h conjugate directions are something like orthogonal directions, but think something, okay, just for understanding sake, you can assume something like that. Okay, so how does this method, how will this work? Will this work better than Newton's method, better than steepest descent method? Okay, so that's the question. So it's loading. Oh, okay, so that is the idea, okay, behind those methods. We can call that as conjugate directions method. So if you want to program, you need to write the steps what you need to do, so that writing the steps is written here. Calculate g of 0. D of 0 is equal to minus g of 0. Step size alpha naught equal to, okay, this is a formula similar to what we used in SDM. So using that, x of k plus 1 formula, this is also similar to what we did in SDM. After this, after you get x of k plus 1, calculate g of k plus 1. Okay, so calculating g of k plus 1, remember, the ideal condition is that g should be equal to 0. But when g is a vector, okay, even in a scalar, you can never get equal to 0. So if that is small enough, smaller than some tolerance value, then that x of k plus 1 you got is equal to the x star. In which case you have to stop here. Okay, this is the stopping criterion. That is, the g is less than some small value. That tolerance, this tolerance, it is left to you to note. Okay, sometimes we okay, that's user discretion, not user's discretion. Okay, otherwise, if the gradient at that point is not small enough, then you calculate the next direction from the definition of conjugate directions. The definition of conjugate directions. Okay. Oh, there is quite a lag between my writing and you writing and you seeing. Okay. So once you have d of k plus 1, again you go through this. D of k plus 1, if you have, you calculate alpha of k plus 1, x of k plus 2, etc. This is a iterative circle, iterative procedure till the stopping criterion is satisfied. All right. So that's how the conjugate directions method works. That's how the conjugate directions method works. So what again I can show you one demo in MATLAB, but let me take one more step, then show you the demo. See, suppose you know one direction d of k, you think. Calculating d of k plus 1 is not that easy because this is one equation. D of k transpose h d of k plus 1 is one equation. And if d might have n number of components. Okay, n number of components it will have. Like g, right? So how do you find all these n components? So that's a bit of a problem. So what improvement people did to the conjugate directions method is they came up with the idea of how to find out the d automatically by using a formula which can be implemented easily in MATLAB. Okay, so the steps up to that point are same. If g of k is less than epsilon, stop. You have found the x star. Otherwise, you go on to calculate d of k plus 1, and how you calculate this beta of k, which is a correction factor, by using this formula. Okay, again derivation is there in books. I will not go into the derivation. You take it for granted. So calculate that correction factor. This d of k plus 1 is same as minus g of k plus 1 plus one correction factor into the previous direction. Okay, to get the current direction or direction in current iteration, you have to use the current gradient and the previous direction multiplied by with one correction factor beta k. So that will give the latest, the direction in current iteration, which is same as what you may get in directions method. What you will get in this directions method of the previous slide. Okay, so this is how you automate. Now you put all this into the formula in MATLAB. It will run and it will give you the it will give you the minimizer, right? So how does it work? So let us very quickly see that. That's the very last, I think. One minute. Be there. I'll share the screen. First, I'll run the program and then share the screen because all of it is not running simultaneously. All windows I am not able to show you simultaneously. So the same window I have shared now, the same function is there, but now let us think that we want to solve this problem by CGM, conjugate gradient method. So this is our starting point. Okay, so now the direction is same as minus g of 0. Okay, this one direction which I have showed you now. You can see the mouse movement, right? The 2 points are there. X of 1 came from X of 0 by going in the direction of G of 0. Now what happens next if I use conjugate direction? Conjugate direction, okay, which I got using all that procedure. So the conjugate direction points towards X of 0 and I reach there. For a quadratic function, I reached a x star by Newton's method in one iteration. By conjugate method, I needed 2 iterations. But what I avoided was taking a H inverse. I can even avoid H. Okay, let me stop sharing this, go back to that. I can, you note that I avoided taking H inverse, but I still needed H, right? I still needed H. So again, people did research on that and found ways for avoiding this, for even avoiding how to take using H. Okay. So anyway, this formula is an approximation. There are other ways of calculating the optimal step size. And in this formula, G of k plus 1, okay, there is another formula, G of k plus 1 transpose plus G of k by something, D of k plus 1 something, right? So there is a formula that's in book. So by doing that, you can avoid even having to calculate H. Okay, so that way you can avoid even calculating the H, thereby speeding up. Remember, Newton's method might take one iteration, but calculating H and H inverse is going to take longer. That is the costliest step in terms of computational time. So if you can eliminate that, these more iterations by other methods will take actually less time than Newton's method, like conjugate gradient method. So that is why it was voted as the one of the top 10 performing algorithms of the 20th century. Okay, it came much before 21st century, before our 2000. Okay, so that was one of the best algorithms of the 20th century. Better, in some ways, better than Newton's method, in many ways. Okay, so that is that. Now there is this dynamic optimization problems. All right, so yeah, there is dynamic, like I told you, that missile problem that is not so easily solvable. That's a very different kind of optimization problem. So that involves knowledge of dynamic. See, we started with unconstrained classical optimization basics of unconstrained problems. Then we came to constrained optimization with constraints. Okay, all those are known as static optimization problems. Okay, now there are dynamic optimization problems. This missile guidance problem is a dynamic optimization problem, but it has lot of applications, not just in missile guidance, in many other applications. Okay, like for example, what should be the optimal rate of fishing so that you should catch the maximum number of fish, without which, suppose you have a fishing contract for 10 years. If you are not going to catch the maximum number of fish, then you will be in loss. Correct. But on the other hand, if you overfish, the fish is going to become extinct. So, what is the maximum rate of fishing that can be done without driving the fish to extinction? Okay, so that kind of problems are also dynamic optimization problems. Or think of this. Suppose you are nowadays there are a lot of diabetic people, right? Lot of diabetic people, but so many people have to need to use insulin. You need to inject insulin, right? But if you don't have insulin, your sugar will shoot up. But if you inject too much of insulin, your sugar will go down. Okay, low sugar sometimes being more dangerous than high sugar, right? So, what is the optimal amount of insulin that you need to inject? Okay, so that's also a dynamic optimization problem which has been studied. So, that is another class of problems, another method that will take something quite some time. You think more than half an hour or 1 hour, maybe depending on our timetable or schedule or time and all that. Maybe we can start, but also these are there. I have to. This is another presentation. Okay, somehow it is here. So our presentation ends here. Actually, first session ended now. Okay, this is up to here. Okay, when I give it to you, I'll delete all this up to 31. Slide 31 is presentation 1. Then second presentation is wait 1 minute. So Aparna, I can take 5 minute break.
Sir, shall we continue the same topic, that is dynamic optimization, tomorrow?
Sure, that also is okay. But you remember, I was supposed to do 3 presentations. This is just the first presentation.
Sir,
I have
actually,
another.
yes, sir, agree. But for participants, right from 9:30 a.m. to till now, so I think to understand, to digest everything, we need certain time, sir. So if you don't mind, shall we continue tomorrow for dynamic optimization?
Sure. Tomorrow. That see, by the time I can put all these slides also, or I'll stop here. Some another topic will take tomorrow, like the gradient free optimization will take tomorrow. If time is there, we'll do that
Yes, sir.
neural network training, etc. Actually, optimization is a what to say, yeah, vast to see, right?
Yes.
I also learned all these things over a period of many years. Okay, so I don't. What so if people participants are finding it a bit difficult, I think that's very genuine, right? So I rushed through all this as if I learned it in 1 day or 2 days or few days. I also took a few years to learn all this. and all these MATLAB programs I showed you. Only after getting some reasonable kind of knowledge and programming knowledge, uh, I carefully chose the examples to match what I was claiming. So all that was there. So you are right. Actually, all this you have to really, really be very sharp and very attentive at the highest concentration to pick up all this.
Yes, sir.
So anyway, I
Okay.
hope it was useful. So tomorrow morning 11:30 we'll meet. Is it?
Yes, sir.
Okay. So very nice. Thank you for hosting. So tomorrow morning 11:30, right?
Yes, sir. Yes, sir. Thank you, sir.
Thank you.
Thank you for today's session, sir. It was quite very interesting. We came across to know about the different methods like Newton's method, then conjugate CGM, conjugate gradient method, and everything. Step by step, you taught them nicely. So thank you very much, sir, for such wonderful session. Thank you all the participants for your active participation. We need your active participation. So hope tomorrow you will cooperate with us. So all participants are requested to kindly fill attendance link and feedback link. So thank you to everybody, and thank you, sir. In spite of your busy schedule, you have shared your knowledge, your information, your deep study related with this optimization techniques. Thank you. Tomorrow we will be there sharp 11:30 a.m. So thank you, sir, and thank you to all.
Yes, thank you everyone. Yes, thanks to all the participants.
Yes, sir. Thank you, sir. Thank you from on the behalf of all participants, sir. We are really thankful for you as a resource person for this 2-week STTP program, sir. Thank you, sir.